Hi team, welcome to Wiggins Maths. In this video we're going to be looking at proving something by contradiction. Okay, so this is the only type of proof that is exclusive to the year 13 content. And obviously that means it's going to be a little bit trickier. And it is just a little bit awkward really. But as I mentioned in previous videos, to prove something to be true can be incredibly taxing. So I'm going to run through two very commonly asked exam questions. Okay, and it's not to say that these will appear in any form of examination, but the method is pretty much set in stone. So, first example is we would like to prove this is true by contradiction. So the square root of 2 is an irrational number. Hopefully, we definitely know that this is true. Now, as proof by contradiction suggests, the first thing that we are going to do is we're going to change this statement. Okay, so we're going to look at root 2 is a rational number. Okay, and we're going to try and prove that this is true. And what is going to happen is we're not going to be able to do that. We're going to get to a line in our working out that suggests that it can't be true. And that will therefore prove this to be true because we have contradicted this attempted proof here. So, what does it mean for a number to be rational? It means that it can be written as a fraction. Okay, where a and b are integers and a over b cannot be simplified. It's fully simplified already, and that's really important. Okay, so that's what it means for a number to be rational. It can be written as a fraction. So if I then start working on this to try and get myself to a point where it's going to show that it can't be true, it's going to take a bit of practice. Okay, but I see a square root here. I'm going to square both sides. And hopefully we're okay with that so far. And then I'm going to multiply both sides by b squared. Okay, now what this does is it tells us that a squared must be even. Okay, because it's two lots of something. And that tells us that a must be even. Okay, so if a is even, then that means that a can be written like that, which means a squared is 4n squared. So therefore, from this point, we can say that 2b squared is equal to 4n squared, which means b squared is equal to 2n squared. So, if that is true, then b squared must also be even, and b must be even. So, going back to our original statement, if a is even and b is even, then a over b is not simplified. And if it's not simplified, it means that it is a contradiction to this statement here. Okay, and since we've contradicted that statement, therefore root 2 is irrational by contradiction. So as you can see, it's a little bit different. Some may say strange, but it's entirely logical. We're taking the statement, we're reversing that statement, trying to prove that to be true, and then it will fall down. Okay, and once it falls down, that can't be true, which means the other thing, the opposite thing, must be true. So the other type of problem that we could be asked to prove by contradiction, there are infinitely many prime numbers. Okay, so the first thing we're going to do is we're going to write down a negation statement. Okay, so there are a finite number of primes. Okay, what's it mean for something to be finite? It means we could list them, right? So if we start listing the prime numbers, so the first prime number, the second prime number, the third prime number, the last prime number, we don't know what it is, so we're going to call it P subscript n. Okay, and here's the trick with this one. We're now going to try and, we're going to say that this number n is a natural number. And we're going to say that that is a product of all of these prime numbers. Add 1. Okay, so we can increase a natural number just by adding 1, right? So here's the really, really clever bit. If n is a natural number, then it must, because it's greater than 1, it must either be prime or a product of primes. That's how numbers work, right? It's either a prime number or it can be written as a product of primes. So let's see what happens when we try to show that it's prime. Well, n is greater than the largest prime number because we've multiplied all the primes together and we've added 1. But this was supposed to be the largest prime number, right? So n can't be greater than the largest prime number. So that's suggesting that n is not prime. Okay? So if n is not prime, then that must mean that it is a product of primes. And if it's a product of primes, that means that we can divide it by a prime number. So I'm going to divide it by Pn. So if I divide n by Pn, what do I get? Well, I get P1 multiplied by P2, multiplied by P3, multiplied by Pn, add 1, all over Pn. Now, what does this statement actually tell me? Well, those cancel. So it's going to leave me with a product of primes plus a remainder of 1. So it has remainder of 1. Now, you may think that's a big deal, right? But if it has a remainder of 1, then it means it cannot be written as a product of prime numbers. So n is not a product of primes. So we've now shown that it's not prime and it's not a product of primes. Now that doesn't make any sense whatsoever because every single natural number is either prime or a product of primes. So that suggests to us that there are infinitely many primes by contradiction. Now, as I've said, this will take quite a bit of getting used to. It's quite challenging, but the statement is always the negation of the original statement, and then you try to prove that to be true, and something won't work eventually. So you can pick up a few marks by starting out the problem. Okay, so as always, by watching this video, it doesn't instantly mean you'll be able to do it. You will need to practice this. As I've said already, these are the two most common things that you're asked to prove by contradiction. The more you practice, the better you will become, and of course, Amateurs call it genius, masters call it practice.